In the last video, we talked about how to describe a particular transfer function. For example, big hz equals to big yz divided by big xz. Using this kind of a ratios, right? You have a numerator and then a denominator, right? This is a description in what we call the z domain, right? And this kind of a polynomial representation can be factorized to give you a representation that's based on poles and zeros. So poles are basically just the roots of the denominator, and then zeros are basically the roots of the polynomial in the numerator, right? So you can represent a transfer function in either way, right? And this is sort of in the z domain, and we talked about the relation between z domain, the z transform, and also the Fourier transform. And what I was telling you is that the Fourier transform is a special case of the z transform, right? And that special case is when z, the complex number z, actually has a length in the complex plane that's unity. So the Fourier transform is basically the z transform on the unit circle, right? On the unit circle, the z transform is equivalent to the Fourier transform, right? And then we talked about several properties of z transform, for example, region of convergence. And we looked at several examples. The region of convergence for causal signal or causal transfer function, right? It's going to look like that kind of thing. The region of convergence contains the infinity, right? So it's pointing outward, right? And then the region of convergence is bounded by the pole with the largest radius, basically. It's bounded, right? And then we talked about this particular example that's sort of anti-causal, right? For anti-causal signals or transfer functions, the region of convergence is like pointing inward, right? It contains zero, and then again it's bounded by the poles with the smallest radius, actually, right? The region of convergence. The region of convergence cannot contain any poles because the poles are the roots of the denominator. At those poles, the denominator becomes zero, so the transfer function becomes infinity, and that's not converging. So. And then we looked at several properties of poles and zeros for some typical system, right? And we came up with these kind of conclusions. So if you need stability, then the region of convergence must contain the unit circle. And we actually gave a mathematical proof that's sort of grabbed from Wikipedia that gives you a bounded input, bounded output stability, right? And then if you need a causal system, then the region of convergence must contain infinity. And the transfer function will be a right-sided sequence. Right-sided sequence means that the amplitude on the negative time side is all zero. So if you need an anti-causal system, then the region of convergence must contain the origin, and then the transfer function must be left-sided. And then if we need both stability and causality, which is usually the case for when designing filters, right? We want our filters to be stable, bounded input, bounded output, and usually we would like to have causality. We would like to have our filter to have causality. Then all the poles of the transfer function must be strictly inside the unit circle, right? By requiring the poles of the transfer function to be strictly inside the unit circle, we are basically saying that the region of convergence must contain infinity, which gives you a causal system, right? And then because all the poles are strictly inside the unit circle, which means what? Which means the unit circle itself is actually inside the region of convergence. So that will give you the stability, right? So for stable and causal systems or filters, right, the transfer function must have this kind of property, right? So all those properties about the poles and the zeros and the z transform or z domain representation of the transfer function actually give us some idea about how to design filters by carefully placing those poles and the zeros in the z domain, right? It turns out to be a quite convenient way for designing filters, for example, right? So let's look at just the unit circle, right? When we are designing filters, most of the time we are concerned about the frequency, right, or the Fourier transform. And the Fourier transform is just the z transform on the unit circle. Let's just look at the unit circle, right? So any point on this unit circle is represented by z equals to e to the j omega, right? A complex number with unit amplitude, right? The length is unity, and then it has an angle, big omega. Big omega, that's represented here as an angle, right? So the basic idea is that if you just look at all the different points on the unit circle, if you just rotate a particular point along the unit circle, right? So when you're actually getting close to the poles, suppose these 2 points are the poles of the filter or transfer function, then your amplitude of the transfer function is going to be bigger, because at poles, at exactly the poles, the transfer function is going to have an amplitude of infinity, right? At the poles, right? Poles, by definition, poles is the roots of the denominator. So at those locations of poles, the transfer function is actually has infinite amplitude, right? So when you rotate along this unit circle, and when you're getting close to one of those poles, the transfer function is going to have bigger amplitudes, right? And then if you are actually getting close to any of those zeros, basically the roots of the numerator, right? Roots of the numerator, at those roots of the numerator, the transfer function basically has 0 amplitudes, right? So by rotating along this unit circle, we can either increase or decrease the amplitude of the transfer function, right? And the angle of the rotation happens to be frequency, right? It's actually a very nice structure, right? So by carefully placing where you want to put those poles and zeros, you can design a filter in any way that you like, right? So that's basically the idea of filter design by pole zero placement, right? So here it's a text that's describing the basic idea. So as frequency evolves around the unit circle, the magnitude of the transfer function increases when getting close to a pole, and decreases as it gets closer to a zero. So poles and zeros close to each other cancel each other's effect. So if you actually put poles and zeros next to each other, so the effect is going to be canceled out, right? And because if you would like to have a stable filter, that's usually the case, right? The unit circle is actually contained inside of the region of convergence, so it's perfectly valid to rotate along the unit circle. So you don't really have to worry about the length, right? Don't have to worry about the length of z. So unit circle is contained inside the region of convergence. Right? Don't really have to worry about the convergence of the filter for stable filters, right? So now let's look at one example. Let's look at the one relatively simple example, right? So here we are actually trying to determine a two-pole bandpass filter with center frequency located at pi over 2, which is basically indicating that the transfer function at pi over 2 must have an amplitude of 1, and then at the transfer function has at 0 and pi must have an amplitude of 0, and we impose one additional criterion, which is the transfer function at pi over 4, right? The transfer function at pi over 4 must equal to the amplitude. The amplitude must equal to 1 over 2. 1 over 2. Right. So let's see how we can actually design this particular filter by placing poles and zeros, right? So because the center frequency is at pi over 2, so we're gonna need a pole at frequency pi over 2. Frequency basically corresponds to the angle on the unit circle, right? So at pi over 2, we'll need a one pole, right? And because all the poles for any kind of causal and a stable system has to be inside the unit circle, strictly inside the unit circle. So the length of this pole, the distance of this between this pole and origin, cannot be larger than unity. So assume the length is r, right? And then we place a pole at rj, right? And another thing that we have to remember is that all the poles and the zeros has to happen in conjugate pairs. That's one of the results from algebra. Basically, if you have this kind of rational polynomials, rational functions, I mean, and then the coefficients are all real numbers for all of the polynomials. Then the roots of all the polynomials has to happen in conjugate pairs, right? So if you have a pole, at this location, then there must be another pole that's at the conjugate location, which is basically here, right? So if you have pole or zero that's lying on the real line, then the conjugate pair, the corresponding conjugate value is also on the real line. So you don't really have to worry about sort of happening in pairs, right? Because it's a real root. But for these kind of complex roots with the non-zero imaginary parts, then you have to be careful about placing them in pairs, right? If you have a root here, then there must be another root here, right? And then let's look at the second requirement. The amplitude at 0 and pi has to equal to 0, right? So which means what? Which means 0 and pi is actually a root of the numerator. It's a 0 of the transfer function. It's a root of the numerator. So let's just place two zeros. 1 0 here, right? And its corresponding conjugate pair is also here, right? It's the conjugate of 1 is still itself, right? And then let's place another 0 at pi. That's here, right? And again, its conjugate is also itself, right? So we have two zeros, right? We haven't considered this condition yet, but let's see, based on this kind of a placement of poles and zeros, what's going to be the transfer function, right? The transfer function is going to look something like that. Big G means a constant scaling. That's the gain, basically. The gain allows you to control the amplitude of the filter in the passband, right? So what's actually the gain? It's just going to be a constant, right? And then because you have two zeros, one is at 1, the other one is at -1. So the numerator is going to look like that. Z subtract 1, that's the root at 1. And then z plus 1, that's the root at -1, right? And then you have two poles, one at rj and then one at -rj, right? So the denominator is going to look like that. It's z subtract rj and z plus rj, right? Z subtract rj accounts for this pole, and then z plus rj accounts for this pole, right? And we can simplify the equation, and then the transfer function is going to have a form that looks like that, right? So because we are sort of particularly interested in Fourier domain representations, right? So all we have to do is to replace z with e to the j omega to actually convert it into frequency axis, right? Frequency domain. So big Hz becomes big He to the j omega, and then big G, z squared becomes e to the 2j omega, subtract 1, right? And then z squared becomes e to the 2j omega plus r squared for the denominator, right? So that's going to be the basic form of our two-pole bandpass filter, right? But we have two numbers that's not being determined yet. One is big G, the gain, and then we have R, right? We know that R must be smaller than unity for this filter to be sort of causal and also sort of bounded, right? But we have two conditions. One is big H pi over 2 equals to 1, right? That's going to give us one equation. And then we have the other equation. That's basically the amplitude of the transfer function at pi over 4 has to equal to 1 over 2. So that's going to give us another equation. So we basically have two unknown variables, big G and R, and then two equations for determining both variables. So now let's try to determine the variables, right? So big H pi over 2 equals to 1 is equivalent to what? If we sort of bring pi over 2 into this expression. So we'll basically replace omega with pi over 2. right? So it becomes 2j pi over 2. That becomes j pi, right? J pi is what? J pi is minus 1, I think, right? It's minus 1 subtract 1. It's minus 2. And then for the denominator, again minus 1 plus r squared, right? So big G actually equals to 1 subtract r squared divided by 2, right? So this is going to give us one relation between big G and r, right? Now let's look at a second condition. That's the amplitude of big H pi over 4 equals to 1/2, right? So let's bring pi over 4 into this formula, right? Replace omega with pi over 4. Then what we are getting? We are getting this kind of thing. Big G times e to the j pi over 2 subtract 1, e to the j pi over 2 plus r squared. And then the whole thing takes the absolute value and the square it has to equal to 1 over 4, right? So basically we're just replacing this condition with another condition, basically that the square of the left hand side has to equal to the square of the right hand side. That's 1 over 4, right? So that's basically using the second condition. And then we can do some algebra. So because e to the j pi over 2 equals to j, basically it's equals to j. So it's g squared, j subtract 1, j plus r squared. The whole thing takes the absolute value and then square it, right? Now you have to sort of look into how to do algebra with complex numbers, right? How do you actually get the square, right? The length of a complex number. So for this thing, j subtract 1, if you want to get the length is actually square root of 2, right? Because the real part is like minus 1, and then the imaginary part. So where it's the real part is minus 1, and then the imaginary part is what? It's also 1, right? So the length of that vector is square root of 2. So if you square it, then it becomes 2, right? And then the same is true for here. So the stuff in the absolute value and then square becomes 2 divided by r squared subtract 1. So this part corresponding to this part, right? And then g squared equals to what? G squared equals to, because we have this relation already, so g equals to 1 subtract r squared divided by 2. All we have to do is to square it. And then the right hand side is 1 over 4, right? So now we can sort of expand the equation and do some algebra, right? And we end up with this kind of second order polynomial with respect to r squared, right? So r squared, if you treat r squared as a single variable, let's just replace r squared with some variables, say x, right? So this becomes x squared subtract 4x plus 1 equals to 0. And the roots of this second order polynomial is x equals to 2 plus minus square root of 3. So x is r squared, so basically r squared equals to 2 plus minus square root of 3, right? So that's going to give us values for r squared, right? That's going to give us values for r, basically. But we have to be careful. It actually gives you two solutions, right? Both of them are positive, right? So it's possible, because r squared is positive, so both solutions are possible. But if you actually go back to look at the location of the poles, it must be strictly inside the unit circle, don't forget, right? For the system to be causal and also stable, right? So r must be smaller. The length of those poles, its distance from the pole to 0, must be strictly less than 1. So r must be smaller than 1, right? So r squared must be smaller than 1, right? So if you impose this condition, then you have just the one solution for the r squared, because 2 plus square root of 3 is larger than 1, right? The only solution that's sort of smaller than 1 is 2 subtract square root of 3. So you end up with a solution that's r squared equals to 2 subtract square root of 3. And then if you bring this solution back into the expression for g, what you are getting is g equals to, so 1 subtract 2 plus square root of 3, it's square root of 3 subtract 1 divided by 2. right? So you get a value for g, right? And then because you already have a value for r squared, you can bring it back into this z representation, right? So you have a g value already, and then z squared subtract 1, z squared plus r squared becomes, this is z squared subtract 1, z squared plus r squared equals to what? 2 subtract square root of 3. So now we got this is our solution in the z domain. This is our solution for the for the transfer function in the z domain, right? So we have actually solved the problem. But we are not done yet, right? We are not done yet. The reason is that usually you would like to implement this particular filter in the time domain. So we need to come up with a recursive formula that can be implemented in the time domain, right? In the previous video, we talked about how to actually convert between this kind of a z domain representations and time domain representations, right? How do you actually convert this to that? And also back and forth, right? Back and forth. These two representations are actually equivalent because you can sort of convert between them, right? So don't forget, big H equals to what? Big H equals to big Y divided by big X. That's the z domain output divided by z domain input, right? So now we have exactly the same kind of a situation, right? So big H equals to big Y divided by big X, right? So now we can rearrange all the terms. So multiply the denominator on both sides of the equation. We end up with z squared plus 2 subtract the square root of 3 times big Y. And then the right hand side is basically the numerator. This factor g times z squared subtract 1 and then times the numerator, big xz, right? But don't forget that we need the expression to be in terms of the z to the minus 1's power, right? So if you actually go back to look at our representation, it's z to the minus 1, z to the minus 2, that kind of thing, right? A minus sign actually means that when you convert it into time domain, it means sort of subtracting something, right? And subtracting, it's a shift to the right, right? So basically, it's gives you a causal implementation, for example, right? So in this particular case, we have to sort of divide both sides of the equation by z squared. So it becomes 1 plus 2 subtract square root of 3, and then z minus 2, right? And then times big Y. And then square root of 3 subtract 1 divided by 2, 1 subtract z minus 2 times big X, right? So now we can start to sort of convert it into a time domain representation. So YZ, big YZ convert into multiply 1 is big YZ, convert it into time domain, you get small yn, right? And then 2 subtract square root of 3, z minus 2, becomes 2 subtract square root of 3, y, and subtract 2, right? Convert it into time domain. And the same thing happens here on x, right? This is a constant. 1 multiply big X converting into time domain gets x, small xn. And then z minus 2 times big X converting into time domain is x, small x, and subtract 2, right? And then if we actually rearrange all the terms, yn, the output at the nth time step equals to, this is the input, right? Square root of 3 subtract 1 divided by 2, xn subtract 2, right? This, and then move this whole thing to the right hand side, subtract 2 subtract square root of 3, yn subtract 2, right? So this is going to give us a time domain implementation for this particular filter, right? So now let's look at this particular transfer function in Matlab and see if it's indeed what we wanted, right? We're gonna just reuse the S3 script, right? So now let's try to type up this particular transfer function as a function of frequency. Let's say O goes from like minus pi to 0.01 to pi, right? And then big H equals to square root of 3, right? Square root of 3 subtract 1, and then the whole thing divided by 2, and then multiply with. So in the frequency domain, big Z can be replaced with e to the j omega. So exp e to the j omega. J is 1i times omega, right? And then because you have a square on it, multiply 2, right? And then subtract 1, right? So that's the numerator. And then dot divide. Then z squared exp again 1i times o times square 2. So and then plus 2 subtract square root of 3, right? And then that's gonna be our transfer function in the as a function of frequency omega. So now we can plot it. Let's just do like 2 subplots, 1, 2, 1, and then plot, normalize the frequency, and then the absolute value of h, right? And then subplot 1, 2, 2, and then plot pi, and then unwrap angle of h, right? So now let's just execute this block. Oh. Right. So that's the amplitude response, and then that's the phase response for this particular bandpass filter, two-pole bandpass filter, right? And then does it actually satisfy all our requirements, right? So big H pi over 2, that's 0.5. Normalized frequency is like a 0.5, right? Must have an amplitude of 1, right? That's 1. And then 0 and pi must have an amplitude of 0. So 0 and pi has an amplitude of 0, right? And then the amplitude at pi over 4 must be equal to 1/2, right? Pi over 4, that's probably here, around here, right? That's 0.5. So it is indeed the bandpass filter that satisfy all those conditions, right? And Matlab also provides a collection of tools to design filters, and all those tools are collected in an application that's called FDA tool. So if you type FDA tool in the command window, it's gonna give you a graphic user interface for designing filters using different kinds of methods, right? And you have the buttons on this side is sort of the method that you can use, right? So for this particular video, we're gonna just look at the pole zero editor, right? So it allows you to actually create filters by placing poles and zeros in the complex domain or in the Z domain. So if you want to create filters using this pole zero editor, you can just click on it, and then it's gonna give you this kind of a interactive interface to design your filters, right? So in the bottom, it's sort of the complex Z plane, and then in the top, on the top, it's the amplitude spectrum of the resulting filter from this plane. And then you can choose to view different kinds of things. So this is the amplitude response of the filter in terms of dB, in log scale, right? And then you can also look at different kinds of things. For example, for now it's amplitude response, and then phase response, right? And then amplitude and phase response. So if you click on that, it's gonna give you this kind of a combined diagram to show both the amplitude and phase from this particular filter design. So this is actually, let's look at a simpler pole zero filter, the one that we just created, right? It has just 2 poles and 2 zeros, right? So if you want to edit this pole zero diagram, you have a bunch of buttons here, right? So this button allows you to create add poles or edit poles. This allows you to add or edit zeros, and then this allows you to delete everything, delete poles or zeros. So let's click on it, and then we can just select or choose a region, right? Once you have selected that region, then everything inside of that region disappears. That's by you can do that just by clicking on the delete button and then drag your mouse over the region that you want to delete everything, right? So that's gonna be let's try to enter the parameters we want to sort of use for this pose zero placement. So the first number we're gonna put into it is the gain. So what's gonna be our gain? The gain is a big G, right? It's the square root of 3 subtracted 1 divided by 2. So square root of 3 subtracted 1 and then divided by 2. That's 0.366, right? So let's just enter the gain. 366. Right. That's gonna be our gain. That's 0.366, right? And then we'll need to sort of put some poles and zeros into it, right? So let's first add zeros first. So we're gonna add let's click on the zero button. So this add zero button. We're just gonna place one here, right? That's one of the zeros, right? No, this is the pole. No, I got it wrong. This is zero. So this is zero, right? So let's delete this one. So if we want to add zeros, click on this button, right? We have 1 0 here, and then click again, another 0 here, right? So if you want to sort of be more precise, here is the magnitude and angle of each of the points that you just clicked. So the magnitude that I clicked for this particular 0, it's not exactly 1, so I want to change it to like exactly 1. And then the pi angle is supposed to be pi, right? So I'll just put pi here, right? And then for this particular 0, let's also try to make it more precise, right? So the radian is the angle is correct, 0 radian, but magnitude is not exactly 1. So now we have two zeros, right? We have two zeros, and then we are gonna need to add some poles to it, right? The poles, where are our poles? It's the poles are at rj and minus rj, these two conjugate pairs, right? And r is what? R squared equals to subtract the square root of 3. So r equals to the square root of that. So the square root of 2 subtract the square root of 3. Right? It's a 0.5176. So let me add a pole. It's about here, I think. And then I need to conjugate to it, right? So 0.5178, 0.5178. 5178, right? And then the angle is supposed to be pi over 2, right? That's going to be the angle for these two poles, right? So now you can sort of see right away the amplitude and phase response for this particular two pole filter design, right? So that's the amplitude response in terms of dB, right? And uh, at mid frequency, so this is in terms of kilohertz, right? It's not exactly in terms of the uh, normalized frequency yet. But it doesn't really matter. And then in the mid frequency, you can sort of see the passband, right? And then at 0 and pi, normalized frequency 0 pi, the amplitude is sort of extremely small, right? So that's sort of the same as our filter, as our previous plot, our own plot, right? For this plot, maybe so in this plot, let's try to sort of plot it into dB log 10, and then 20 times this. So just close this figure. The range of the y is slightly off, so subplot 1 to 1, right? Y lim, let's go from like minus 90 to 0. Right. So that makes the figures more sort of compatible with this figure, right? Even though the ratio of the plot is slightly off, but these two plots are actually equivalent, right? So you can use this F. It's called a FDA tool, filter design and analysis tool, to uh, to to design a filter by placing poles and zeros in this kind of a pole zero diagram, right? And once you have finished computing this filter, you can choose to export it. So you can export it. There's an option in the file menu that allows you to export the filter, right? And then it allows you to export to a bunch of choices, either workspace or different kinds of ASCII files, mat files, or so we're just going to use workspace, and then export as coefficients. You have another choice. We'll just choose the default coefficients, and then it's going to have numerators and the denominators, right? Numerators are basically just the coefficients in the numerators, right? So basically it's just those coefficients in the for polynomials, for the numerator polynomials, and then coefficients for the denominator polynomials. So basically it's just it's basically those alpha and beta values, or b or a values. In Matlab they use b and a, right? So b are the coefficients for the numerator, and a or alpha is are the coefficients for the denominator. So here we are just gonna export it as numerator and denominator coefficients. So this tool actually automatically converts the pole zeros into coefficients. Basically, they expand the factorized polynomials into these kind of expanded polynomials. So we're just gonna export it. So we're gonna have two new variables in our workspace. One is called NUM with big N, and the other one is gonna call DEN with big N. Override the variables. We're gonna override if there is any previous variables defined using the two names. We're gonna override it and export, right? So now in our workspace, we're supposed to have two new variables. One is called DEN, that's the coefficients for the denominator, and the NUM, that's the coefficients for the numerator, right? So if we want to look at the DEN, that's sort of the coefficients for the denominator, and then NUM, that's coefficients for the numerator, right? And Matlab actually allows you to convert those coefficients back to pole zeros, right? And there are several functions. It's called a ZP to TF, for example. That's the zero and poles to transfer function, right? So it allows you to convert zero poles to transfer function coefficients. And then you also have the opposite function. That's TF to ZP. See, it's actually making the suggestion TF to ZP. So if you do help TF to ZP, then it allows you to convert those coefficients back into pole zeros, right? So you can do this kind of a back and forth transform by using these two functions. So now NUM, that's the coefficients for the numerator, right? So if we do help TF to ZP, then it's going to take numerator and the denominator, the coefficients for the numerator and denominator, and then it's going to return three parameters: zeros, poles, and then the gain, right? So ZPK equals to TF to ZP, right? And then we're going to use our numerator and then denominator that was exported from this particular application, right? And then let's take a look at what are the ZPK values. So Z, the zeros, we have two zeros, right? -1 and 1, right? That's the two zeros. And then P, we have two poles, right? We have two poles. So that's the value of R, right? So we computed R by taking the square root, because we have the R squared to subtract the square root of 3, so we computed R by doing that, right? And then what's actually the value of k, right? K is the gain, that's the g. So square root of 3 subtracted 1 divided by 2, that's exactly 0.366, right? So if you want to sort of do this conversion in the other way, so if you want to convert zpk to coefficients, you have zp to tf, right? So you have zp to tf, right? So you have zp and k. And then if you want to convert it into coefficients, in the numerator, that's b, and then in the denominator, then you can do that. You can use this function. So that's the b, right? That's the a, right? Coefficients for the numerator and then coefficients for the denominator. So if you compare it with NUM 0.366, some numerical error, of course, right? But the imaginary part is extremely small, so this number is about the same as this number, 0, right? And then this number, about the same. And then if you compare it with DEN, and A should be about the same, right? So it also allows you to uh, to 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 do this kind of conversion back and forth, right? And then there's another tool that allows you to visualize pole zeros from the coefficients. It's called FV tool. So suppose we have the coefficients for the numerator and the denominator, that's b and a, but we want to look at the pole and zeros for the filter that's computed by this represented by this numerator and denominator coefficients. Then we have this FV tool, and then it's called a frequency visualization or filter visualization tool, right? It allows you to use those coefficients to compute and display all the locations of the poles and the zeros. So let's take a look. And then that's the output, right? It's a pole zero plot with a complex z-plane. That's the real part, that's the imaginary part, and you can sort of see where the poles, the zeros are, right? That's the two zeros, and then that's the location of the two poles that we used for creating that filter. So if you actually want to compare it with with this pole zero plot, it's supposed to be about identical, right? Because they are actually identical. It's exactly the same actually, right? So Matlab also provides a set of tools for you to design filters by pole zero placements, right? And this tool is called FDA tool, right? And it actually has a graphic user interface, allow you to design the filter interactively. So far we have talked about zero phase and linear phase filters. We haven't discussed in detail what the minimum phase filters are. But in a previous video, I used FIRGR, this Matlab function, to generate a minimum phase filter. Right? That's the script that I used for generating that minimum phase FIR filter. Right? But what exactly is a minimum phase filter? We haven't sort of talked about that in detail yet, right? So here's some formulas I grabbed from Wikipedia. So one of the important properties of a minimum phase filter, especially for seismologists or for geophysicists, is that a minimum phase filter minimizes the so-called group delay. So it minimizes the shift of the energy of a particular waveform. Right? So it's not gonna sort of, unlike a linear phase that's gonna shift the entire energy of the energy of the entire waveform by a certain amount. It's gonna minimize the shift of the energy, right? And and a group delay is measured by what? It's measured by the derivative of the phase of the filter with respect to frequency. It's basically d phi d omega. So let's look through the example that's given on the Wikipedia page. Right? Suppose you have a zero. Right? Your transfer function has a zero that's given by a. So you can write a as its absolute value times e to the I theta a. Theta a is sort of the angle of that zero, right? And theta a equals to arg a. And if you have this zero, for the transfer function, then the term that's contributing, the terms that this 0 is actually contributing to the numerator of the transfer function is just the 1 subtract a times z to the minus 1's power, right? That's the term that's contributing to the numerator by this particular 0. Right? And then we can sort of study the phase angle contribute the phase angle of the transfer function contributed by this particular term, right? So phi a represents the phase angle contributed by this particular term of the numerator, right? We can take the argument of this particular complex number if we actually bring the expression of a into this representation, right? And then we can sort of analyze it, right? And we end up with this kind of formula, right? That's sort of the effect of this particular 0 to the phase angle of the transfer function, right? Now we can compute the group delay. The group delay is just the effect on the group delay caused by this particular term is just taking the derivative of phi a with respect to omega, right? Again, we can sort of do some trigonometry and algebra, right? And then reorganize all the terms, right? And simplify it, and we end up with this particular expression, right? So that's sort of the group delay. That's the group delay caused by this particular 0, right? So suppose a, this particular 0, now suppose the a, this particular 0 is actually located inside the unit circle, right? If it's located inside the unit circle, then we have the absolute value a that's smaller than 1, right? Now imagine we reflect this 0 with respect to the unit circle. That's basically taking a, converting a to a minus 1, and then take the conjugate, right? If we replace a, whose length is smaller than unity, with a minus 1 conjugate, right? If we replace it with its reflection with respect to the unit circle, then we're getting, then the absolute value of a is going to be larger than unity. So for if a is lying within the unit circle, this particular 0 for the transfer function lies within the unit circle, then reflecting that 0 with respect to unit circle is going to increase the group delay. Which means what? Which means that if you want to minimize the group delay caused by a particular 0, you would like to have that 0 stay inside the unit circle. And that's just for 1 0, right? But the phase caused by those zeros are additive. So for this particular 0, it's 1 subtract a z to the minus 1. Suppose you have another 0 that's called b, then the other term is going to be 1 subtract b z minus 1, right? You're just multiplying them together, and then the phase angle for each of the term is additive, right? The total effect is just for a and b is just phi a plus phi b, right? So the effect on the phase is going to be additive. If you want to minimize the effect on the group delay, then you would like to have all the zeros of that transfer function to stay inside the unit circle, right? So a minimum phase filter has this kind of property. It has all its zeros lying inside the unit circle, right? That's called the minimum phase filter. If you have a filter that has all its zeros also lying within the unit circle, then you have a minimum phase filter, right? And then let's look at the implication for such a minimum phase filter, right? So suppose we have a stable and a causal filter, that's transfer function, that's big HZ. Since big HZ is stable and causal, so all its poles should lie inside the unit circle on the complex Z plane, right? So now let's look at the inverse of that filter, right? The inverse of that filter is going to have a transfer function that equals to the inverse of big H. So So the inverse of the filter is just the 1 divided by the transfer function of the filter, right? That's called the inverse filter, right? It's basically just gonna undo any effect that's gonna caused by that's caused by that filter. It will undo it, right? So that's sort of that's what we call the inverse filter. So what's actually the relation between inverse filter and the filter? If you apply your filter first to an input signal, and then followed by that you apply the inverse filter, right? So it's basically hz multiply h inf z, then you get unity, right? So it's basically unity multiply the z transform of the input signal, right? So you get the input signal back, right? So the output of this the output of this filter and then inverse filter, this operation is going to be the input signal again, right? That's sort of the meaning of the inverse filter. Now suppose big Hz is actually causal and also uh, stable. Then all its poles are gonna lie inside the unit circle, right? If you take the inverse of that transfer function, then the denominator becomes the numerator, and then the numerator becomes the denominator, right? So for the inverse filter, its poles are gonna be the zeros of the original filter, big H, right? And for the inverse filter, its zeros are gonna be the poles of big H, right? So it's for the inverse filter, the poles and the zeros are gonna be just the opposite of big H, right? Poles becomes zeros, zeros becomes poles if you take the inverse, right? So if big H, if we also require big H to be not just the stable and causal, but also minimum phase, then we have what kind of consequence? It means if it's minimum phase, it means that all its zeros also lie inside the unit circle, right? And then for the inverse filter, the poles of the inverse filter is the same as the zeros of big H, right? Since big H has all its zeros inside the unit circle, so the poles of its inverse filter are going to be inside the unit circle. So it means what? It means big H IMV, the inverse filter, is also causal and stable. So that's one of the consequences for having a minimum phase filter, right? So if you have a minimum phase filter, then the inverse filter is also going to be causal and stable, right? So both the filter itself and its inverse are causal and stable, right? That's one of the consequences. And the minimum phase filter is a very good property. Is a very good property, and if we can actually get minimum phase filters, it can be quite useful in practice.